locality-based neural solver for optical motion capture. We present a novel locality-based learning method for automatically cleaning and solving optical motion capture data. Our method can solve large body motions and fine multi-fingered hand motions. Our method demonstrates robustness in handling simultaneous occlusions, long-duration occlusions, and outliers, which are frequently observed in hand markers. We show the markers on the right hand. Next, we demonstrate our pipeline. Different from previous neural-based methods that overlook the relations between neighbor markers. Our method leverages marker locality by identifying neighbor markers with stable distances across the whole motion. It can help the network to efficiently recover the occluded marker's location and better represent the motions of the corresponding body parts. As a preprocess, we fill occlusions and clean outliers before feeding data to the solving network. For occluded markers, we first use EDM optimization to solve for marker positions based on their distances to corresponding neighbor markers. Then use a bidirectional recurrent neural network to fine-tune the positions. For outliers, we identify them by detecting abnormal values in the acceleration curve. Then we remove the sequence near the outlier and fill the gap using spline interpolation. To remove the global transformations of markers, we explicitly calculate the local coordinate systems of body and hands and align them using the transformations between local and global coordinate systems. Our method yield more stable results compared with those using rigid body alignment. Next, we solve for motions. We construct a heterogeneous graph consisting of a marker graph and a joint graph. We first perform convolutions on the marker graph to extract the local features of the markers, then perform convolutions between the marker graph and joint graph to transform marker features to joint features, and finally transform them to result motion. We augment the dataset by generating synthetic data with distribution close to the real data. We randomly add occlusions gaps to the clean data based on real occlusion probabilities and occlusion gap distributions. We also add shifts to simulate outliers. Subsequently, we compare our method with baseline methods. To compare with the ground truth, we render the skeletons and overlay the ground truth's skeleton onto those generated by solving methods. Our method solves motions that are closest to the ground truth. Optimization-based methods, such as Vicon, lack the learned prior knowledge for the occluded markers and motions, which fails to accurately solve motions when large numbers of markers are occluded simultaneously. Our method outperforms other neural-based methods for two reasons. First, our method better reconstructs the positions of occluded markers, providing a better input to the solving network. Second, our solving network extracts local features of each marker and joint, which aids in generating motions that are close to the ground truth. We present a qualitative comparison of hand motions. Markers on hands are susceptible to occlusion and shifting. Our method demonstrates robustness against those noise, and accurately solves the motions. In this case, the marker of little finger is occluded. Moreover, the markers of the middle and ring fingers are incorrectly labeled. In this instance, all markers, except the one on the thumb, are occluded. Consequently, Vicon fails to solve this motion. We present a demo using the motion solved using our method. Our method can solve large body motions and fine multi-fingered hand motions and is robust to occlusions and outliers. Thank you for your watching.